Back today, I've got my buddy Sam with me, and we're going to talk about this reactive speaker project we built a while back for our controls class in college.
Yeah, what's up, guys? This was a pretty fun project. It ended up being a lot more interesting and engaging than we anticipated.
Really. So at a glance, it was just kind of a speaker and a mic. But in reality, this is a full feedback loop system. The speaker itself listens to itself through the microphone, and it constantly adjusts its own output to balance the volume from the mic's reading.
Exactly. As the mic was picking up the sound, it was converting it into voltage, and which was then put into decibel values. And then we had to put that into our PID controller thing, and then so the system can check how far off it is from the value and constantly adjust to it in real time to the speaker's output.
And the key is it's not just reacting once, it's a continuous loop. So this is sampling at a rate, I think this was zero point zero 0.01 seconds, every zero point zero 0.01 seconds, if I remember correctly. And the mic hears the speaker and the controller adjusts the output. And then the mic hears itself and it hears itself change and the process repeats. And it begins this dynamic balancing act.
All right, so here's how we set up the system. We used an Audio-Technica microphone, but instead of a standard XLR output, we built a custom XLR to RCA cable. The soldering was straightforward, positive went to positive, the short prong on the RCA adapter, and both negative and ground went to negative, which is the long prong. For the output side, we used the Edifier R1280T bookshelf speakers. They took an RCA input, and we fed that signal from the Quanser Q8 USB data acquisition board, specifically from the analog outputs 6 and 7. The yellow microphone cable was connected into the analog output 7. We also set up a sound shield, just a cardboard and a bed sheet, to help isolate the mic from the background noise. For calibration, we placed the microphone exactly 1 foot from the speaker. We sent a 60 hertz tone through the system and recorded the amplitude recording from the mic at several different voltages, inputs to the speaker. To protect the speaker from potential damage, we placed a saturation block before the HIL right analog block that kept the speaker's input voltage safely between 500 and 650 or millivolts. For our decibel reading, we used the equation decibel 20 times log 10 V1 over VO, where VO is our reference voltage of 0.001 volts, measured peak in the microphone. Once we had that data, we could basically match a target decibel level to both the microphone's voltage reading and the sine wave amplitude that we needed to send to the speaker to make that happen. And just as a note, while our system is designed to work at a variety of mic distances, we ran calibration at 1 foot because that distance gave us the most sensitivity to change. That 1 foot distance was always included in our test ranges as well. All right, so here's what we found in the results for the different controllers. The P controller was definitely the most responsive and it gave us the best range, but there was a trade-off. The sound quality was pretty harsh. When we switched over to a PI controller, the sound quality improved dramatically. It was much smoother and overall more pleasant to listen to, but the trade-off was the range. We only got a reliable operation between 0.5 foot and 2 feet. We tried a PD controller, but honestly, this was terrible. The range dropped even further, 0.75 to 1.5 feet. The sound quality was terrible. Finally, we tested a PID controller. This was interesting. It gave us smooth, clean quality we liked from the PI controller, but the range was on par with the P controller. The responsiveness was also really great, similar to the P, which made it feel really balanced. Now, here's why this happens. Compared to the P and PD controller, the PI and PID controllers are more smooth and stable because of the integrating term. That term continuously adds up the error over time, which helps reduce steady state issues, things like background noise or outside voices. It also helps reduce the oscillators or jittery behavior we saw in the P and PD controllers, specifically those graphs. And that's the big deal for the audio-based volume control. You want precision and stability, something that reacts to changes in volume quickly, but also holds steady state without overcorrecting or overshooting. The PID controller ended up giving us that balance, which makes it the most well-rounded option. Now, here is the final mic self-stabilizing system with the Edifier speaker.